Okay, I think we will go ahead and get the ball rolling here, Caleb, and some more folks will trickle in, I'm sure, in the introduction. So, good afternoon, everyone, and welcome to the Carbon Solutions webinar series, where we highlight work taking place across our company and with our partners. I'm Veronica Wild, a research scientist at Carbon Solutions, and I'm glad that you've all joined us today, let alone the day before a holiday. So, thank you. This month's webinar is focusing on how geothermal, concentrated solar heat, and air source heat pumps each contribute to renewable heat generation across the United States. And today's session will be led by Caleb Geissler, who will walk us through process level models and geospatial comparisons to illustrate when and where each technology performs most effectively. He will also explore how different evaluation metrics, including the levelized cost of heat and the levelized cost of carbon removal, influence technology preference and deployment decisions. I did want to note for everyone that this meeting is being recorded. The recording, along with our previously archived webinars, will be available on the Carbon Solutions YouTube channel following today's session, as well as emailed out to all of you. So we encourage this to be a collaborative conversation. While we will reserve time for Q&A at the end, please feel free to submit questions throughout the presentation using the chat function. Thank you again for joining us today, and I will go ahead and pass it over to Caleb.
All right, thanks, Veronica, and thank you again, everyone, for being here. So like Veronica said, today I'm going to talk about some work that we've done here at Carbon Solutions over the past year, along with some of our collaborators on comparing different technologies for generating renewable heat. So just some very high level background, over the past few decades, there's obviously been a lot of work into decarbonizing electricity. But another really important thing that we want to decarbonize is heat. And like many things, that is easier said than done. So a few things make heat a little more interesting and difficult to decarbonize. So for example, one of those is that temperature matters. So unlike electricity, where kind of every electron functions the same way, different technologies require different temperatures of heat in industry, and so therefore we might need different technologies to produce heat at different temperatures. Heat is also not easy to directly transport, so typically it would have to be generated on site, and that means that there's strong spatial dependence on its performance. We also have that many industrial heat demands are constant or nearly constant, and that means that it leads to inherent difficulties in variable renewable resources like solar. And then last, over the past, over a century, there's been plenty of time for fossil fuel-based heat to have, technological and performance improvements, which can help lower costs that technologies for renewable heat didn't have the benefit of. So with that said, so we wanted to focus on a few specific technologies for generating renewable heat. So at a very high level, we used process models for geothermal, concentrated solar, and an air source heat pump. And we wanted to compare these geospatially across the continental United States using two different metrics. So one is the levelized cost of heat, so purely economic, and one is the levelized cost of carbon removal when that heat is coupled with a sorbent-based direct air capture system. And we chose this as our second metric because low temperature DAC, which we assumed required heat of 105 C, is indicative of many low temperature demands in industry. And we also then have the importance of the emissions that we might incur that are captured in the LCOR metric that aren't captured in the LCOH metric. And I'll get into those details on future slides. But beyond just comparing, where in the country these different technologies are preferred, we also wanted to look deeper into the specific parameters that influence which of these is preferred. So a little bit more detail about our heat sources. So we consider sedimentary basin geothermal. We use locations from Carbon Solutions Scott Pro database, and we use the GenGeo model to generate cost estimates for those. For concentrated solar heat, some of our collaborators modeled parabolic trough collectors and developed regression equations for different classes of direct normal irradiance and air temperature. And using those regression equations, we're able to calculate the optimal amount of thermal energy storage that should be coupled with this across the country. So the more thermal energy storage you add, the higher your capacity factor, but also the higher your capital costs. So that's a trade-off that varies geospatially that we're able to capture. And then for the air source heat pump, we built a process model to model its performance based on an average air temperature. And here we optimize the approach temperature. So we assume that the approach temperature is the same for all units. So if you have a higher approach temperature, you can have lower capital costs because you have a higher thermodynamic driving force, which means smaller heat exchangers, but you'd have slightly higher electricity costs due to reduced efficiency. So this is another trade-off that varies geospatially that we're able to capture. So like I said, we have these two different metrics that we care about, shown here on the right. So our LCOH metric is our simplest. It's just the capital cost of our heat technology times a capital recovery factor, which would be the same for each technology, plus its operating costs, divided by the heat, the rate of heat it produces, which we assume is 20 megawatts for each, times its capacity factor. So again, this is a purely economic metric. For our LCOR, we also include the capital costs of the DAC facility that it would be coupled with. And then we also have both the actual amount of CO2 that the DAC facility would capture minus the amount of CO2 emitted from electricity consumption. So like I said, that's important because for our air sourced heat pump, we assume that it's connected to the grid, so grid emissions can play a really important role. We also ignore the operating costs of the DAC facility in this metric because we know that the operating costs will be the same for each of these, and we're more interested in just comparing which heat source is preferred, not necessarily getting a super accurate value for LCOR. So that means that the LCOR values we find will likely underestimate the true LCOR value. With that, I'm going to dive into some results first, going one at a time across these three different technologies. So here on the left, this is a map of the locations where the sedimentary basin geothermal resources in the US are sufficient to provide 105C heat. So the regions in red are, it's technically able to provide that heat, but it's just very expensive. So it'd be more than $150 per megawatt hour. And then in other regions, mainly in the southern US, you have better performance. But again, not very many regions across the US that you're able to use sedimentary basin geothermal directly to produce 105C heat. On the right, same idea, but for LCOR. And you can kind of see similar trends of regions where it's extremely expensive and regions in the south where it's a bit better. So the next heat technology is our concentrated solar. So obviously big difference here is that concentrated solar in principle is available anywhere in the country where you have space to put your collectors. You'll see that there's some regions on these plots that are white. Those are just regions for which regression equations weren't developed, but you can still see the general picture. So when we look at LCOH on the left, unsurprisingly, concentrated solar is better in the south where it's sunnier, and especially in the southwest. And then when we look at LCOR, the similar trend is observed, but it's a little more strong. And that's because in our LCOR, the amount of CO2 captured itself in the DAC process also has weather dependence, so that performs even better in the southwest. So that's why we see that stronger dependence, and then LCOR being a little bit worse in like the Pacific Northwest and in New England. And then our last technology to investigate, oh, actually, no, before that, sorry. Another interesting thing to note about the concentrated solar is the capacity factor. So like I said, we, for each location, determine what that optimal capacity factor is. So this is just a histogram of, in all of the grid cells across the US for which we calculate this, how often we have these different optimal capacity factors for our different metrics. So for LCOH, when we're looking at just costs, we see typically around 25 to 45%. But when we look at LCOR and we include the capital costs of the DAC facility, a much higher capacity factor is preferred to help pay off that capital. And so that's probably more indicative of if you're coupling generating heat with an industrial process that you want to run as often as possible, you would expect to want a higher capacity factor. So now on to the air source heat pump. So once again, there's some places that are white. In this case, this is just regions where the data source we used for electricity price didn't have a value. But for LCOH, again, you can see in areas like California and like Massachusetts area, which have higher electricity prices, the LCOH is higher, but you don't have the same like weather-based performance that you would see in concentrated solar. So while higher air temperature does mean a more efficient heat pump, that is kind of dominated by the cost of electricity. In the right plot is the LCOR. Things are a little more interesting here. So like I said, we assume that the air source heat pump is connected to the grid, and therefore in regions, in this case, it would be state by state is how we have the grid emissions. So in states that have very high emissions intensity of their electricity, you might net emit CO2 because you're using such dirty electricity, or have such little net CO2 sequestration that your LCOR is, above $1,500 per ton. So we see that generally in the northern Midwest of a lot of states where it's just, this would not be a good idea. And so we see that it tends to be the Western US and kind of Northern New England where an air source heat pump has the best LCOR. So this was each of them individually. So next I'll just show in each location in the US, just which one is preferred. So kind of what we see is that where sedimentary basin geothermal is good, it is the best regardless of the metric we use. But again, that's relatively few locations across the US. In the rest of the US, we see that concentrated solar tends to be preferred, with a air source heat pump sometimes being preferred at northern latitudes depending on the metric. So for LCOH, again, the primary metric for the heat pump is the electricity price. So we see in more northern latitudes where our concentrated solar isn't as good, regions that have a lower electricity price tend to prefer an air source heat pump. When we look at LCOR, all those states in the Midwest that have high emissions are always select concentrated solar, and then it's more state by state based on the state emission factor for their electricity. And again, northern New England and a few states in the Pacific Northwest would prefer an air source heat pump. So like I said at the beginning, though, we also want to dive more into beyond just which is preferred where, into kind of the parameters behind the performance of these different technologies to understand, what's going on here. So we do this by a series of binary comparisons between the technologies. So the one I'll start with is the sedimentary basin geothermal versus concentrated solar. So basically, geothermal is primarily the performance is primarily a function of the reservoir depth, transmissivity, and the subsurface temperature gradient. There is some dependence on things like electricity and price and emissions because it does need some electricity, but that's generally dominated by the geologic parameters. So these contour plots on the right are basically describing, for a given location, the reservoir depth and transmissivity, and then we have different plots for two different examples of the subsurface temperature gradient. And the color is basically showing how the DNI class, so the kind of the range of DNI that you would need for concentrated solar to be preferred. So the way to interpret that is like these red regions is your geothermal resource is so good that no matter how good your DNI is, geothermal will always be preferred. In contrast, in these blue regions, your geothermal is so bad that if you have any sun at all, which everywhere in the US does, you would prefer concentrated solar. And then the gray region is just a a combination of parameters that would not be sufficient to provide 105C heat at all. So in that case, geothermal isn't even an option. And then these different X's show examples of actual locations in the US. So this is not by any means all the locations, it's just those that fall very close to this specific temperature gradient being plotted. And then we do this for both LCOH on the top and LCOR on the bottom. So kind of what this is showing is that especially if you look at the temperature gradient of 40 C per kilometer, it's pretty straightforward in most locations that it's very obvious whether geothermal or concentrated solar will be preferred. There are relatively few locations that kind of fall in this narrow band between these solid colors that it actually matters how good your sunlight is. We also see pretty minimal dependence on the metric here. The plot varies a little bit between the two, but in general, if you look at LCOH and it tells you based on LCOH, this location far and away, geothermal is better, that will likely be true as well when you use LCOR. So then the next comparison is between geothermal and a heat pump. And so again, we use the geological parameters, but instead now we look at the break-even price of clean electricity. So we're not dealing with any of the emissions with the grid here. So again, the red regions on these plots is your geothermal resource is so good that even if you had completely free electricity with zero emissions, geothermal would still be cheaper than an air source heat pump. And then in this green region, even if you had to pay more than $500 per megawatt hour for your electricity, it's still better. An air source heat pump is still better than geothermal. And then there's this larger band between them where it actually matters how expensive that electricity would be. So again, because we're looking in this slide at clean electricity, we see also minimal dependence on the metric we use. So instead of showing both metrics here, this is all for LCOH. And instead we look at two different air temperatures. So again, the higher air temperature means that the air source heat pump performs better. But even with that, we also see relatively minimal dependence in terms of these plots of the decision between geothermal and a heat pump doesn't depend that strongly on the air temperature. It's much more driven by the geologic parameters and the price of the electricity. So then kind of the next and last combination of parameters to look at is the concentrated solar versus the heat pump. So in this case, we once again look at the break-even price of clean electricity. And we do this for each metric. So in this gray, this is for the LCOH. So unsurprisingly, see that as your solar resource gets better, you need cheaper and cheaper electricity for the air source heat pump to be preferred. Eventually getting to the point where if you have very high DNI, even free electricity, even with free electricity, concentrated solar would still be preferred over a heat pump, similar to the comparison between the geothermal and the heat pump. One thing you'll see on this figure is that there's a lot of these like little boxes. That's just an artifact of the classes of the DNI and air temperature that get assigned to a given regression equation for the concentrated solar. Just means that kind of a bucket of parameters end up with the same cost parameters. So that's just why you see those boxes. When we look at going from LCOH to LCOR, the break-even price of our clean electricity increases, and that's favoring the heat pump. And that's because, the heat pump here is connected to the grid, so it's able to have a high capacity factor automatically. Whereas with the concentrated solar, in order to have a higher capacity factor, you have the additional cost of installing thermal energy storage. So you can see some interesting things on this plot. For example, if you can buy clean electricity, if your price of your electricity is $100 per megawatt hour, when we're looking at LCOH, the fact that it's clean doesn't even matter. So at that price, concentrated solar is always going to outperform air source heat pump. But if you looking at LCR and you care about your emissions, well, then it depends on how good your solar resource is. If it's really good, concentrated solar will be preferred to a heat pump. But if it's really bad, it'd be worth paying $100 per megawatt hour for clean electricity. So again, this plot would look different, well, if you included emissions. But again, for this comparison, we focus just on break-even price of clean electricity. So this is kind of the results I wanted to show. Just going to wrap up with some high-level conclusions. So what we saw is that the metric that we use, whether it's the LCOH or LCOR, can determine which technology is preferred. That is most prominent for the air source heat pump, where the grid emissions intensity has a pretty big role in terms of the LCOR. So it's really important when choosing a renewable heat technology to decide which is the appropriate metric to use for evaluation, or maybe use both. We see that across the U.S., where geothermal is good, it beats other technologies, but that's relatively limited area. I'll note that in our assumptions for our DAC facility that we assume is coupled with this, we assume that we need to provide 105 C heat. If that temperature was lower for a different DAC process or just a different process altogether, that could increase the amount of the U.S. that sedimentary basin geothermal would be available. We see that where we don't prefer sedimentary basin geothermal, concentrated solar tends to be preferred across much of the U.S., with a heat pump only really being preferred in northern latitudes with cheap electricity, if we're looking at LCOH. And if we're looking at LCOR, it also has to have clean electricity, which is really, we see only in kind of northern New England and a few states in the Pacific Northwest. Obviously, these exact results will change over time as the grid evolves, but we do see that in general, concentrated solar tends to be preferred in many locations, which we think is pretty interesting. So that's all I have. I'll be happy to take any questions here, and you're welcome to reach out. My email is there if you want to follow up with any questions as well.